Not more cheating than helping.
Which, yeah, is really learning, but really the question is, do you actually want to learn it? You don't.
Right, and I think part of that's on the teacher.
Yeah.
When you're a teacher, you're going to get a room full of kids who couldn't care less about what you're teaching, and job one is you got to make them care.
And ChatGPT is not going to actually help people care either anymore, and I think that's where the human element is so vital in a teacher's role. It's one, like you bring a lot of energy to this, what you're teaching, and that's what makes
Right.
it.
Otherwise, you'd all just go to sleep, right?
Yeah. So anyways.
All right. So this next chapter, we are jumping into the grammar of our logic now. We're going to jump into all the symbols that we're going to be using to write out the logical structure of some sentence, and we're finally going to be able to give an exact definition as to what we mean by sentence. What ultimately does a grammar do? What does the English grammar do? It gives us the rules and symbols for generating sentences that we call English sentences. So we're going to come up with the rules and symbols that we're going to use in logic for generating logical sentences. That's big picture what this chapter is going to be about. Now, quick review of the important verbiage so far. So first off, we're pretty much ending propositional logic and now moving into what's called predicate logic. So let's remind ourselves, what is propositional logic? What's a proposition?
It's a sentence that can either be true or false.
It's just something that's either true or false, not both. In this class, we've been focusing on sentences. But proposition in general is just anything that's either true or false, not both. One or the other. Then we've been talking about sentences that encode propositions, which also in English we call them statements. Sentences that are either true or false, we call them statements. Up until now, we've been using sentence, statement interchangeably. They pretty much mean the same thing. And that's been our intuition for what the author means by sentence. We'll give an exact definition of what he means by sentence by the end of today. But that's been our intuition so far. Some English sentence that you can call true or false, that's what he's meant so far. Basically what we mean by sentences. And then we've been talking about sentential connectives or logical operators, one and the same thing. What are our sentential connectives we've been interested in?
Atomic sentential
And or truth functional sentential connectives is what you were after.
Oh, yeah.
And or not implies an equivalence. Those are the 5 big ones.
Right.
And so far, all we've been doing when I give you some sentence is you've been using big letters to represent chunks of the sentence that are complete sentences, and then symbols for these logical operators for how they combine.
Yeah.
If I were to say, let's symbolize something like all men are animals and there's a bluebird in the sky, we might have symbolized that as all men are animals and there's a bluebird in the sky, and that's as much as we could do so far. Which isn't much. It's very coarse for all the words I said, and we want to break down and start looking at all the substructure that exists in sentences like that I told you. So here's an example of a sentence I want to look at. Let's look at a sentence, everything is either red or not red. So pick anything you want in the universe. It's either red or it's not red, right? True sentence. Everything is either red or not red.
Yeah.
Now let's think about how we might symbolize this. How could I symbolize this? Is it everything's red or not everything's red? No, this says something different. This says everything in the universe is red or everything in the universe is not red. Not pick a thing out of the universe and it's either red or not red.
It's also the inclusive or, so both of them could be true.
So both of them could be true. The point is, we can't symbolize this sentence like this.
It
doesn't get the structure.
It's for all
Logically,
x,
that
it's
cannot
either red
be
or not
true.
This says, pick anything you want in the universe, and it's either red or not red. This is true. This says, we live in an entirely red universe, or we live in a universe devoid of any red things.
Right.
Interesting.
So it should be for all x, it's either red or not.
Right, so the point is, using our symbolic notation, we have no way of breaking this down yet. And we just would have to represent this as a red or not red sentence. And that's all we could do with something that has all that structure.
Yeah.
Yeah.
We want to be able to break down pretty much any English sentence that you can construct and get all that fine structure. So far, we're kind of stuck. Now we're going to develop beyond that. And, well, so far, what did we have in our grammar? What were the symbols we were allowed to use? We would use capital letters to symbolize sentences. Outside of that, we definitely use parentheses to specify precedence. We see things like A or B comma, implies C, or whatever we wanted.
Yeah.
So we've been using parentheses, we've been using letters to symbolize sentences, and then we've been using sentential connectives. We're going to stop using these letters to represent entire sentences, and we're going to start breaking down their substructure.
Gotcha.
So, our grammar is going to consist of parentheses, we're going to use that the same way we know not. Our sentential connectives, not, and, or, implies, and equivalents. And then, these sentences we're going to start breaking down into terms, predicates, and quantifiers. The terms, those will be either the constants or the variables, will represent our terms, very similar to the way we use this language in like mathematics.
Yeah.
Variables and constants, those are your terms. Predicates, we have some experience with predicates up till or in the past classes, but for now, if you're not familiar with predicates, you can think about this as properties that objects have or relationships that exist between objects will be described with predicates. And then our quantifiers will only have two of those, universal and existential. And then between that, this will capture our entire grammar for how we're going to symbolize sentences. Every symbol we write down will be one of these 5 things, and you can stick in that category. Until we introduce the equal sign, which will be adding identity to our logic. That will be the last symbol we don't yet have. And then that will be all the symbols we use in logic. Okay, so we already got parentheses, we already got sentential connectives. Next on the list is terms. So we're going to jump into terms and figure out exactly what we mean by terms. All right? Terms, intuitively, they're the objects that we're talking about. They're the subjects of your sentences. That's what the terms are going to be. The actual things that we're talking about. So
A,
intuition,
B, and C.
go ahead.
So it's, the terms are A, B, C. In the sentence you have.
Well, these sentences were saying something about the terms. If I say the sky is blue, what was my term? The sky, that's the object I'm talking about. I'm stating something about the sky.
Yes.
So that would be an example of a term that maybe showed up in that sentence. Each sentence has a term. You know your sentences, every sentence you have has a subject and a predicate.
Yes.
You're predicating something of your subject. You can think about the subject as acting as the term. And that's what all these sentences must have had. Terms and predicates.
So the term is always a noun. To like, in that sense.
A better way of saying it is
Is
the
it always
noun
the
is
sentence?
always a term.
Noun is always a term.
Yes, but when Aristotle did this, he did call the subject the noun and the predicate the verb. That's what he called it.
Right. It's just could a term be a different noun in a sentence that's not the subject, or just always?
Yeah, it could be a direct object, would be a term.
Direct object could be a term.
Yes.
Okay.
Okay,
No problem.
so just the objects that you're talking about, the things that you're talking about. The terms. Terms are broken up into variables or universals, and then constants or particulars. So when we're symbolizing some sentence, if it uses a universal like men, we're going to use a variable to represent that. If it says Jack, that's now a constant, that's a particular thing. And so Jack would be a constant, men would be, we represent with a variable, as an example. So typically our variables will represent our universals and our constants will represent our particulars. For those of you coming from philosophy, we basically use variables to represent what Aristotle called secondary substances, and we use constants to represent what he called primary substances. Individual particular things, and then classes of things would be your variables. As a matter of notation, common convention, we will use lowercase letters at the start of the alphabet to symbolize our constants, and we will typically use lowercase letters at the end of the alphabet to symbolize our variables. You can almost always guess from context whether it's a constant or it's a variable. Very similar to your algebra classes. Good so far? Okay, so let's jump into this sentence again, but this time identifying our terms. So this is saying for everything in the universe is red or not red. Well, everything, that's a universal, so we're going to represent that with a variable. So I'm going to rewrite out what that sentence says, actually marking the variable with some symbol. So what's it saying? It's saying for every x, using x now as my variable, x is red or x is not red. Resymbolizing what this sentence says, marking the variable. Good so far?
Okay.
Now, your first thought might be, how's that helping? This is a lot messier than that. Is marking the variables just making it harder to read the sentences, harder to consume what it's saying? Here's another example that makes it clear how useful variables can be in helping you consume some sentence. Look at this sentence. For any numbers x, y, and z, x times y plus z is equal to x times y plus x times z. Try restating this sentence without using variables. You'd have to say something like, for any three numbers you choose, the product of the first number with the sum and the second and the third is equal to the product of the first with the second, summed together with the product of the first and the third. It becomes a nightmare to try and follow what that sentence is saying. And it wasn't that long ago, even in academia, that the textbooks you would use didn't mark their variables inside the text. And so if you go do some old math problem, here's a typical problem you might see in an older math text. It might say something like, find a number whose product with 3 is 9 more than 6. Kind of hard to consume. Now let's just rewrite this out, identifying the variable. What's it saying? So it's saying find a number, that's a universal, so we're going to symbolize that with the variable. So it's saying find x such that, what? Such that its product with 3, 3x, is 9 more than 6. So you take 6 and you add 9 to it. That's what I'm saying, find x such that 3x is equal to 6 plus 9. This is way more consumable. You can look at that and instantly think, oh, 5.
Yeah.
Getting it from that, much harder. So just marking the variables already makes consuming what would otherwise be some dense sentence much nicer. In some cases, it may make it a little bit harder to read, but there's a lot of cases out there where it makes the sentence much more consumable. Just marking out your variables and your constants. Okay. So with that, what exactly is the definition of a term? I'm going to give you the definition. We're going to do a bunch of examples, and I'll give you the definition again, and I think you'll get it. Because there's two parts to it. Okay. A term, what's a term? It's an expression that results in the name or description of some object when the variables are replaced by names or descriptions. It's an expression that results in the name or description of some object when the variables are replaced by names or descriptions. You do not have to use a variable, and you can just name or describe it directly, or you can use variables in your name and description. Okay, that's a mouthful. Let's look at an example. Isaac Newton. Is that a term? First off, there's no variables in it, right?
Yeah.
So it can only be a term if it names or describes someone. Does it name or describe someone?
Yes.
Yes, so it's a term. Okay, the greatest mathematician of all time. Does that name or describe someone?
The whole thing?
Yeah, the greatest mathematician of all time. That's one and only one person. Who that is, you don't know, but it describes someone.
Yeah.
I could say, the last person who walked in this classroom.
Yeah.
That describes a person. We may not know who it was, but that doesn't change the fact that that describes a person.
Whittles it down to one thing.
Right. It's a particular
Singular.
thing. A singular.
Yes.
Particular. Two.
2.
Is that a term?
Yes.
Yes. It names something. Namely, 2. X plus 7. Is that a term?
I would say no.
No. Wow. You think about it.
Does it name or describe something? No, because it has a variable in it. Does it name or describe something if we were to replace a variable with names or descriptions?
Yes.
Once I replace the x with some number, pick it, 5, now this names one and only one number, namely 12. If I replace it with 20, it names one and only one number, namely 27. So this is a term. When I replace all my variables with numbers, it gives me only one number.
So what is a term?
So it is a term.
Wait, it is?
Yes. So what is a term? It's something that either names or describes something directly, or it's an expression that results in the name or description of some object when the variables are replaced by names or descriptions.
Gotcha.
Okay.
Let's do more examples. You tell me whether or not it's a term. 2x is greater than 9.
It's a predicate. It's a relation, isn't it?
Is it a term?
So it's
It returns true or false. So is it true or false a term?
That results in...
no, it doesn't turn.
If I give it a number and evaluate this, does it result in a number?
Yes. It's a term.
No, it does
So let's plug in 7. 14 is greater than 9. What number is that?
it doesn't return a number.
It doesn't return a number. It states a relationship between numbers. This is not a term.
Oh,
This is not a number.
I see.
If I replace all my variables with some number, it does not result in describing some number. Not a term.
So true or false is not a term.
Right. So that is going to be a predicate. Things that return true or false once you give them their terms are what we mean by predicates.
Right.
Okay, let's try another one. X squared plus y squared minus 17.
Yes.
Yes, once you give it an x and a y, you can evaluate that expression, and it's just going to be a number. It's just a term. The sky is blue.
No.
No. True or
No,
false?
the sky is a term, but this is a statement about a term. It's not just a term.
Yes.
Statement about a property of a term.
Sure, it's saying some property that the sky has,
Yeah.
but it's not describing just the sky. It's not just the sky. It's not the term.
Okay.
Okay.
Okay. The fattest man in state X.
Yes.
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 Once I give you the state, it is now describing one particular person. If it's Arizona, this is now talking about the fattest man in Arizona. And that's only one person, one particular thing. So it's a term. X loves Y.
No, not
Statement.
Once you know X and you know Y, now this evaluates to true or false. It doesn't tell you, it doesn't give you a particular object.
right.
So, not a term. Bob.
There's so many Bobs. So it's so hard to say.
Yeah,
Maybe
because
no.
it's a name, like Isaac Newton is.
Unless
It's a
I'm
name.
referring to a Bob that I know of.
There's always going to be a little bit of contextual things to it.
Yeah.
But yes, Bob. If Bob shows up in a sentence, that's a name of someone.
Right.
It's naming someone.
Within context, we know what you mean by Bob.
You know what you mean by the name. Just like sometimes we use that symbol for O, sometimes we use it for zero.
What if we're to say like humans? Would that be a term?
No.
Okay, so.
Oh,
Bob is
sorry.
just
Yes, sorry. Yes, humans would be a term.
Oh,
And it would be represented with,
a conglomerate of just all the humans.
We're all X or what? Or
humans is a term, and we represent it with a variable. Ish.
Oh, well.
You kind of need a predicate and a variable to get at humans. You'll see how we deal with something like humans.
Okay.
Because we'll deal with freshmen a lot. And freshmen's kind of in that same category. We'll have a lot to say about freshmen.
okay.
Got it.
And you can replace all those with humans to see how we deal with humans. But yes, we're going to use variables to represent humans. But there's a tweak to that we need predicates to help us specify it's a human.
I guess what I'm looking for. And
It's going to be all X such that the human predicate applies to X.
Right.
Oh,
That's it. Okay. And then 7 minus 4 times 8.
Yep. That's true.
Yeah, that's a term. Name's the number. Namely, 24. Okay, so that's it for terms.
Sweet.
Feel like you have a good grasp on terms?
Yep.
Yeah.
They're just the objects we're talking about.
Yes.
Okay. Now let's move on to predicates, the next part. So we already did that. Jump into the next one. Only have 2 left and we're done. Okay, what's a predicate? It's an expression that results in a proposition, something that's either true or false, when provided the appropriate number of terms, maybe one, maybe many. The way I always describe a predicate is it's a proposition valued function. It's a function such that if you give it its terms, it spits out a proposition, something that's true or false. Predicates, you can't call them true or false on their own. Once you give them their terms, you can then call them true or false. Our notation is going to be, from here on out, capital letters will represent our predicates. And then we'll follow them up by the terms that they're talking about. If I were to say that Jack likes Jill, I would say the like predicate applies to Jack. Jill also starts with J. And Alice. Okay. Jack likes Alice. The like predicate applies to Jack and Alice is the way we'll symbolize it. So capital letters will represent predicates. Lowercase letters will represent terms.
Okay.
If they're lowercase letters at the start of the alphabet, they're meant to represent constants. If they're lowercase letters at the end of the alphabet, then they're meant to represent variables. Because you can also pass variables into predicates.
Liking is okay.
So there's two types of predicates that show up a lot. There's predicates that only take one term predicates. We typically call those properties. That's somewhat used language. On the other hand, there's two-term predicates that take two terms. Those are called relations. And those are ubiquitous in pretty much every field. Everyone talks about two-term predicates as relations. In geometry, we recently were talking about equivalence relations. The state of a type of relation, a property that a relation has, or a set of conditions a relation satisfies. Okay, so let's give you some examples of predicates. Here's an example. Is blue. Is blue is a predicate. Once I give you the term, this returns something that's either true or false. If I throw in this desk is blue, that is false. If I plug the globe in, right there, the globe is blue, returns true. Is blue is a predicate. Another example, greater than 3. Question, greater than 3.
Yes.
Doesn't make sense. But if I say 6 is greater than 3, you can now say true. If I say 2 is greater than 3, you can now say false. But greater than 3 by itself is neither true nor false. Now, as a matter of notation, we put variables in here to signify where the term would go that you plug in. So I would do x is blue, but this isn't the x is blue predicate, it's just the is blue predicate. And I would do x is greater than 3 when I wrote this, but this isn't the x is greater than 3 predicate, it's the is greater than 3 predicate. Or if we're doing one that's a loves predicate, this is now a relation, states a relation between two objects. If I give it Jack and Jill, it returns true. If I give it Jack and Vanessa, it returns false. Once I give it two things. And so we use variables to signify just placeholders, where the terms are meant to go, and whether it's the same term in both those places or different terms in each place.
Wouldn't that imply that x is greater than 3 is also a relation?
X is greater than 3 is a predicate.
Because there's only one variable.
Predicate.
No. It is, wait, not a relation, it's a predicate. It's a property.
Yeah.
It's a property a number has. A property can be, or a number can have the property of being greater than 3. 17 has the property of being greater than 3.
But that's a predicate that has two terms. X and 3.
So the predicate, that's why I said, remember that your x is just a placeholder. It's just syntactic sugar. I could have just as easily put an underbar right here, an underbar right here, an underbar with the 1 there, and an underbar with the 2 there, saying first variable goes here, or first term goes here, second term goes here. We use variables, it's just syntactic sugar.
So when we refer
We
to
can still
variables-
pass variables into the predicate, and that's very different. So if I put this one here, x is blue, when we write out what this predicate is, we might symbolize it with just b. We do not symbolize it with bx unless we're actually talking about the variable x is blue. Those are two different things. Just because I use the x there doesn't mean that that's somehow tied into the predicate. It's just a placeholder. I could have some variable, and now I could be stating that variable, whatever it is. I know it's a blue thing.
Okay, well, it's just.
But the variables,
Questions.
we put them there, but they're just placeholders. So this is not the x is greater than 3 relation. This is the is greater than 3 property. 17 has the property of being greater than 3. 1 does not have the property of being greater than 3.
Oh, interesting. Okay, I think I get it.
Now, what you guys are seeing is that here's a common relation. There's also the greater than relation that takes 2 terms. So there is a greater than relation which takes 2 terms. But there's also the greater than 3 property. And these are 2 different things. I could use this relation to construct this property in whatever system we develop. That's perfectly legal. But 2 different things. Property relation. And don't read too much into the fact that we put variables there as placeholders. It's just to help us keep track of what we're talking about.
We
Okay,
cannot
so I think
consider variables as terms.
So
The variables are not the terms passed in.
Yeah.
They're telling you, here's where you put the terms that you pass in.
So they're sort of a lot like just an intuition for it. They're functions where if it's one input, then it's a property. If it's two inputs, then it's a relation.
Perfect. It's a function that returns a Boolean.
And it also returns a Boolean.
It returns a Boolean, and it's a function.
With one property or two properties.
And internally, we're naming the things that you pass in, x and y. That doesn't tell us anything about externally what you passed in. Externally, you could have passed in a variable that happened to be named x.
Yeah.
Internally, we're calling it x, just as a placeholder for whatever you passed me. Okay, for the programming analogy. Okay, think we got it? Let's try some. Which of these are predicates? X plus 2 equals 4.
Yes.
Yes. Once you replace that x with a number, the result is something that is either true or false. If I replace it with 3, the result is false. If I replace it with 2, the result is true. So it's some expression such that when you give it the appropriate terms, in this case it only took one term, the result is a proposition. Or the way I like to think about it is just a proposition valued function. You give it some terms and it spits out a proposition. It spits out true or false. All right, 2 plus 2. No, that's just a term. X is less than y.
Yes.
Yes, that is a 2-term predicate, which we have the special name relation for. The sky is blue.
Yes. Yes, but it's a 0 term.
Is blue is a predicate. The sky is a term. When I pass a term to a predicate, the result is a
You
proposition.
didn't pass in the term. The term was already there. It's a constant.
Right.
So I get what you're saying, and it's funny because some people describe atomic propositions as 0-termed predicates. We will not use that language, and so in this class, a predicate will always take at least one argument.
Okay. But then that can't be a predicate. There's no
Right, so this is understood that
That's not right.
here's the predicate, here's the object being passed in here. And if we were to symbolize this, we would symbolize it with is blue, that's the is blue predicate, and it's talking about what term? The sky. So maybe little s, and here's how we would symbolize that sentence. The is blue predicate applies to the sky, is the way we would read it.
Right.
And that's how we would symbolize that simple sentence. It's predicating something of that object.
The object being constant.
The object being the sky, some individual particular thing. Yes, in this case, it's a constant.
Huh.
Good?
A little bit.
Okay, so now going back to the sentence we started with, using our predicates now, we can now re-symbolize that sentence. For every x, red applies to x, or not red applies to x. And that's now our symbolization so far. With me?
Yeah.
Okay.
Yep.
Yes.
This is just how we would symbolize this initial sentence so far.
Oh, okay.
Use marking the variables and marking the predicates and the sentential connectives. Now, because now that I have a smaller way of talking about those predicates, I can now get at this structure, the fact that there's an or there and a not there. I have a way of trying to break that up and get at that interior structure.
It's just it's
So
hard
for
to-
every, sorry, that's a comma.
That's what I was going to ask.
Yes.
It's hard to see.
Yep. I brushed it when I wiped something there. Okay, yeah, sorry. So it says for every x, either red applies to x, or it is not the case that red applies to x.
Yep.
Now, notice, x now is the variable being passed in there. We could have said r. We could have said r is x is red, I don't know why I capitalized red, predicate. But the fact that we put x there has nothing to do with the x here. It's just a variable we chose as a name here. Complete accident. So I want to overstress that the is read predicate is the is read predicate, and the X there is just a placeholder to tell us where the term goes. In this case, we happen to plug in X for our term into that predicate. And now, because we know that a predicate returns
True or false, right?
a proposition,
Oh.
we can use
Yeah.
proposition operators on predicates once we give them their terms.
Oh, okay.
So X applying to red is now going to be a proposition, and so negating that is still a proposition.
Yeah.
And oring these together is still a proposition. And so you can use all our sentential connectives here on propositions, and it all works out, or on predicates, and it works out the way you expect.
Can you do logic on predicates that do not have the terms?
Yes. And what you're defining is another predicate. I could have the predicate R is a is red predicate, and I could have B is equal to the is blue predicate. Won't bother with the variable there. And then I can come up with the new predicate W, and my W is going to be the R and B predicate. The thing is red and blue. And since what these return is ultimately propositions, by the time we're ANDing, we're going to be ANDing propositions together. And so it works. And so you can apply your logical operators to predicates because predicates ultimately return propositions.
So you can kind of mess your predicates forever? Like you can have one predicate defined as two other predicates defined as two other predicates? Or
Yeah. You can have one predicate defined in terms of as many predicates as you want. Okay, let's get comfortable with some of this symbolization and point out some of the problems we have in English. So, start symbolizing these sentences. So we'll start with men are animals. First off, what is that sentence saying? Is it true that men are animals?
Yeah.
Is that true?
Yes.
So what does it mean when we say men are animals?
It
For
is
all
true
men, for every man.
So you're saying
Animals.
for every x, let's just use x as our variable. What's it saying about the x?
animal predicate applies to it.
So is it capital A or?
Sure. A for animal, we can do that.
And then-
So you're saying AX like that?
Yep.
Yeah.
So this is saying for everything, it's an animal.
Uh,
That essentially says everything's an animal.
No, you have to say for every x where the man predicate applies to it.
So for every x, then what? For any object, what's this saying?
Oh, okay, I see what you're saying. Okay, so we're actually doing capital M. Wait,
Sure.
Where mx
and then
applies.
our animals would be the A? So you'll-
Sure. We'll use M and A, that's fine.
For
Yeah.
every x, mx implies ax.
Perfect. MX implies AX.
Yeah.
For
So
every x,
if a man.
if it's a man,
Nice.
then it's an animal.
That takes out.
Yeah.
We agree that's what that's saying?
That's
Makes
much
sense.
better, yeah.
Okay, let's try another one then. Men play golf. Is this true? Do men play golf?
Yes.
Yeah.
Yes.
So what's it saying?
Saying
Some men
take off.
play golf.
No, it's not. It's not implying some men play golf.
Is it saying all men play golf or some men play golf?
It's saying all.
Saying all.
And now we're getting into the ugliness of the English language. Because up here, you want to interpret men are animals as all men are animals, and down here, you want to interpret men play golf as some men play golf. Your brain is deciding how should I interpret the sentence in a way that will make it true. So you know how to make it true, and you're choosing to interpret it that way.
Yes, I hate it.
And so Aristotle referred to these as indefinite universals. You're not sure what exactly you're talking about. Are you saying all men are animals or some men are animals? All men play golf or some men play golf?
Yeah. It's all, right?
Which way is it?
All.
Does it matter?
It's all.
It's poorly phrased is what it is. And strictly speaking, neither of those are propositions. They don't encode propositions.
Because of-
Those are both predicates. Strictly speaking, all this is saying is, if X is a man, then it's an animal. And that's all it's saying. If it's a man, then it's an animal predicate. And that's it. And it's not something you can explicitly call true or false.
It's not applying to the universe or anything. It's just.
That's just let's think.
Okay.
And you have to specify, were you saying all men or some men? We'll have more to do with that when we get to quantifiers. But we have this ambiguity in the English language. Now, there is an understood rule in English that, idiomatically speaking, when it's not stated, you interpret it as all.
Yeah.
Common idiom of English. But strictly speaking, it's not there.
It's just not a correct statement, or something?
It's not, strictly speaking, a proposition. It's perfectly okay for your layman in a regular conversation to say something like this. If some philosopher is writing a textbook and he uses as a sentence, men are animals, throw the book at him. He should know better. A philosopher should be as expert in logic as we require a physicist to be in differential equations.
Yeah.
A philosopher misusing logic, like a physicist misusing differential equations. What are you doing? You obviously have no clue what you're talking about. Quit it. Go get educated on foundations, then try writing something. But in its colloquial verbiage, then it's typically understood that when you say something like that, it means for all. But that's not always the case, because as we saw with this one, you instantly interpret it different.
Yeah.
So there is no hard and fast rule for when you're reading English, here's how it is. It's just typically, here's what people seem to have meant. But strictly speaking, what did they say? A predicate, and that's it. Nothing more.
So a proposition, the requirement of a sentence being a proposition is that it has to have only one interpretation.
It returns to your fault.
Technically, the words M-E-N-A-R-E, space A-N-M-I-L-S, do not return true or false. It's only our interpretation of that.
So this is a perfectly valid sentence generated from the English grammar.
Yes. And it's not, it has multiple
The
interpretations.
logical structure that this encodes is nothing more than a predicate. All this encodes is, if it's a man, then it's an animal, that predicate. This neither says all men, strictly speaking, it neither says all men are animals or some men are animals. All it says is, if it's a man, then it's an animal, predicate. Just predicate, nothing more. That's a predicate, that's a predicate. It's stating this implication between those two predicates. Just like anding two predicates together.
Help me get a little tuition for the MX implies AX. Is this a statement that just literally does not apply anywhere in the universe?
Well, it's not a statement, it's a predicate.
It's a predicate that does not apply anywhere in the universe.
I don't know how to answer that. We use predicates to construct our language that we use for all modeling of everything in the universe. But it doesn't state some explicit fact about the universe, because it doesn't state a fact. Because facts are encoded in propositions. This is not a proposition.
That's what I meant to say.
Okay.
Okay.
Yes. In that case, yes.
It's not a proposition. It's a
Predicate.
predicate.
So one-term predicate.
Still getting those mixed up.
It's stating a property.
I-
It's the, if it's a man, then it's an animal property.
So it's a predicate,
Yes.
and a predicate alone does not apply to anything in our universe.
It does not state a fact of the universe. Because facts of the universe are true or false. And so they're encoded with propositions.
Okay. Just want to clear that up.
Right. So to convert this to a proposition, well, we'll talk about that after quantifiers. So we'll have more to say about these types of things. Okay. So now let's move on to our next example. All men are animals. Okay, now that's the one that we first wrote up here.
Yeah.
That was for every x, comma, M applies to x implies A applies to x. All right, let's try the next one. The sky is blue.
It's just that B applies to sky.
Yeah, the is blue predicate applies to the sky.
Yeah.
Now, that is a predicate together with its actual constant, its actual particular. So that's a proposition.
Yeah.
Because it has a particular.
Right, in this case, this was also a proposition. But when I get rid of that, now it's just a predicate.
Okay. And it's because X is just blank. It's like it doesn't.
Right, it's like the x is just blank otherwise.
Like X does. It's because sky is a term.
Yeah, the sky is an action, not just a term, but that works as a way of thinking it.
Yeah.
But a particular thing. All right, let's try another one. Frank is taller than Jack.
I still gotta get sink in. BS is a predicate.
No, this is a proposition.
Dang it,
Oh,
this is-
Is blue is a predicate. The sky is a term.
My brain.
You're taking the is blue predicate, you're giving it the term the sky, and the result is a proposition, something you can call true or false.
Proposition is
I actually had this question about the one that we're moving on to. I was confused when you were talking about like Jack loving Jill earlier and how L applied to
Okay,
both of them.
so let's do this again. So Frank is taller than Jack. What is this saying? This is saying the taller than predicate applies to Frank and Jack.
Right,
Can you write it in between?
but
In the special case, where the predicate we are talking about takes two terms, in the special case where the predicate we're talking about is a relation, it is common practice to write the name of the relation between the two terms, and to rewrite this as Frank is taller than Jack.
okay, that makes
That
a
is
lot
common
more sense.
notation when you
Because-
are
Sorry.
using a two-term predicate. Three-term predicate, that goes out the window. If we were saying between us, the geometry relationship between us applies to points A, B, and C, we would write that as between us, A, B, and C.
Yeah.
Between us applies to the points A, B, and C. And this is a standard way to do it. If I had a 20-term predicate, I would do the name of the predicate followed by the 20 terms that it took in the order that takes it.
Okay. That makes sense. It's just it applying that way felt like I needed to put a parentheses around them, and it was like. they
So that is
both
also
are
common
taller.
notation.
They are both.
So
taller.
rewriting this, a common notation is B parentheses S like that, viewing it with functional notation. And rewriting this would be T, F, J. I actually like this notation
yeah.
better,
Yeah.
but it's not the notation the author uses.
But it's just T applies to F.
T
And J
applies
is
to F and
just-
J. The taller than predicate applies to Frank and Jack. Or in other words, Frank is taller than Jack.
Yeah, but it's specifically Jack is not taller.
No, this one is saying that the Frank is taller.
Exactly.
If I swap the order, now we're saying Jack is taller than Frank.
So it's because of the order of it that you pick
The
up.
order matters very much. Just like in geometry, between us applying to A, B, and C says that B was between A and C.
Yes.
And the order there mattered in which we took the terms. We just named that relation so much we don't bother putting the B in front or giving it some special name.
So as it shows up in the, frick, I'm still confused with predicate proposition. In the sentence, as it shows up in the sentence, that is the order that it should be described in the freaking symbol. I don't know.
That's
As it shows up, like yeah.
I just got a little bit more clearly. This is saying for every x, mark our variable. Then applying to x implies animal applies to x. That's symbolizing that one. The sky is blue. We are predicating is blue of the sky. So the is blue predicate applies to the particular object, the sky.
And we're looking at times when there are two proposite terms, like Frank is taller than Jack.
So Frank is taller than Jack. So the taller than predicate applies to Frank and Jack. This is saying that Frank is taller than Jack. If we
In
were to
that
say the
order,
taller than
yes.
predicate applies to Jack and Frank, that's something very different.
Right, I know, and what I'm saying is that the rule that we're applying here is that as the term shows up in the statement, that is when it needs to show up in the.
We're assuming you understand from context what that T stands for.
Oh, okay, what if it was X and
So let me write out T explicitly, and maybe this will help. Let's write out T explicitly. What is T explicitly? It is blank is taller than. Again, we use variables as placeholders, not because it has anything to do with actual variables you're going to pass in. So T is X is taller than Y predicate. And whatever comes first goes there, and whatever comes second goes there. That's if we were to explicitly write it out. I assumed that you picked up what exactly T meant just from reading it.
I did.
Right.
I just wanted to confirm that the rule applied here is in the order that they show up is
The order that you
the
plug it in.
input.
It's the order of the arguments.
Okay.
Yep.
Confirm that.
That's correct. Okay, Jack loves Beth. How do we write that?
It would be the is loves predicate applies to Jack and Beth.
Yeah.
Would that be?
The loves predicate applies to Jack and Beth, or Jack loves Beth. Both of those perfectly acceptable notations. The prefix notation or the infix notation. Perfectly fine. Okay, George is very fast and strong. How would I symbolize that?
Is fast and strong
J,
one predicate?
F,
Is that
and
two?
S.
That's two.
Oh,
would be-
the and scene. Well, no, it doesn't matter. You're just plugging it in.
No, it would be,
Oh, maybe you're
the fast
too.
predicate applies to George and the stronger predicate.
Right, so the very fast predicate applies to George, and the very stronger predicate applies to George.
Yep.
Now, again, there's no reason that we couldn't have defined some new predicate W, and W is the F and S predicate, and then we could have said W applies to George. This is the next way to symbolize it, so good there. I'm just saying, you can construct new predicates from existing predicates and re-symbolize the same sentence that way as well. But this is definitely the most straightforward way to symbolize it. Rather than saying, well, let's let W equal F and S, and then we'll write that. Saying the same thing, two different ways. Good? Okay, important note, that we've already said a few times, but can't overstate it. Predicates are neither true or false.
False.
Practically are. Predicates are neither true nor false. You can't call them true, you can't call them false.
Because they
If you
have
give them
a-
their terms, now they are true or false.
Yes.
Good?
It's when the predicates have a term with them, or multiple terms with them, and become a proposition that they can be true or false.
Right.
So
You can convert the
only-
predicate to a proposition by giving it the appropriate terms.
Yeah.
Okay,
Isn't
we
that
can see
what
all that
I
case
was
means.
talking about like several classes ago about.
I have no idea.
You were asking if a statement was true or false, and there was an X in it, and I said,
Oh,
no,
probably.
it's a predicate. And you're like, no, we'll get to predicates later. And I'm like, is it not a predicate?
You might have said proposition. I might have said no, it's a predicate. We'll get to that later. But if you said it's a predicate, I said no, that was a lie. Yes, it was a predicate.
You
It was
haven't
like that
recorded.
X is greater than 3 on the slide.
Maybe I'll get to the bottom of this.
Yeah, it's all recorded. You can see if I lied to you. Good reason to record it. Capture all the lies. Okay. Now, the last piece of our grammar that we need to talk about is quantifiers. There's only 2 types of quantifiers. There's the universal quantifier, which is this upside down A looking thing. We read that as for all, or for every, or for each. Or logical equivalent versions of that. But typically, those are the 3 ways you read that symbol. And then the other one is the existential quantifier. This backwards E is typically read as there exists, or there is, or some. Good so far?
There's at least one.
Yeah, some is.
Yeah, so you can think about there exists means that there is at least one. Same thing. Some means, in logic, there is at least one. Some people like some in their intuition to mean more than one. Some in logic never means more than one. It means at least one. Could be more than one, but it's at least one. And that's what some will always mean in this class. Good point. Okay. And now, one way that we can convert predicates into propositions is we give them their terms. Is blue by itself is just a predicate. If I give it this desk, and now I say this desk is blue, now that's a proposition. That's something that's either true or false. That's one way that we can convert predicates to propositions, is give them their terms. Another way that we can do it is to add quantifiers.
Right.
So, let's get familiar with this really quick. I say X loves Y. True or false?
It's predicate.
Bad question. It's a predicate. It's a two-term predicate. It's a relation. However, if I gave it some quantifiers, reading this, what does this say? This says for all x, there exists a y. After you read the existential quantifier, you always say such that in English. For all x, there exists a y, such that x loves y. Now that's something that is true. This says everybody loves somebody. That's something that's true or false. Sorry, I probably said it was true. I meant it's something that's either true or false. It's now a proposition. This essentially says everybody loves somebody.
And that can be, yeah, okay.
For all x, there exists a y, such that x loves y. Everybody loves somebody. That's something that you can now call true or false. But x loves y, that alone you cannot call true or false. Looking at another one. X plus y equals z plus 2. True or false? Bad question. But if I were to say, for all x, for all y, and for all z, x plus y equals z plus 2, now it's something we can call true or false. In this case, false.
Yeah.
Oh, yeah.
Right? It is not true that for all x, for all y, and for all z, x plus y equals z plus 2.
Yeah.
If you were to switch one of those with exists, you could probably, well, with,
If two of them would
if you were to
exist.
keep one with
Whether
all
there
and
exists
two
or
with
not.
exists, then it would not.
I don't know.
There should be a there exists.
Exists for each of them?
There exists for each of them. Will for sure get you a true.
We could do two alls and one exists. It would still work.
We could do two alls and one exists if we're careful about the there exists. If we do it right here, this is still true. This says, for any x and for any y, there exists a z, such that x plus y is equal to z plus 2. However, if I were to put the there exists right here, for all x, there exists a y, such that for all z, x plus y equals z plus 2. No, there is no magical y you can always add to x, such that its result is always z plus 2.
Yeah.
Here, I forgot I want to do these. I even put a box to remind me. I want to do these first before those examples. Sorry. To help you get comfortable reading these. So I'm going to read these, and you're going to tell me true or false in each
Oh,
case.
This is the same thing.
Same thing. So this says for all x and for all y, x plus y equals 0.
False.
True or false?
False.
False. This is saying the sum of any two numbers is 0, which is false. It is not true that for any x and for any y, x plus y is equal to 0. Let's look at this one. For all x, there exists a y such that x plus y equals 0. That one's true. For any x you find, I can always find some y out there such that their sum is 0. Let's try the other one. There exists an x such that for all y, x plus y equals 0.
True.
No.
False. There is no magical x out there you can find such that no matter what I add to it, we always get 0.
Oh, okay.
This says for every x, there is some y such that their sum is 0. This one says there exists some x out there such that for whatever y you add to it, you get 0.
Okay.
Two very different things. And now you capture something very important. Order in quantifiers matters a lot. So this one is big old false. There's no magic x out there such that for all y, x plus y equals 0. All right, let's try this one. There exists an x and there exists a y such that x plus y equals 0. That one's true. You can find two numbers that add together to be 0. All right, just to continue the exercise, let's do this again, but this time with multiplication symbols. So times, 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 repeat. For all x and for all y, x times y equals 0.
No. False.
No.
False.
Is the product of any two numbers 0? No. Okay, for all x, there exists a y such that x times y equals 0.
Yes.
Yes.
Yes,
0.
0. Okay, there exists an x such that for all y, x times y equals 0.
Yes.
Yes.
0.
In this case, yes. 0 is the magical x such that no matter what you multiply by, you get 0. And then finally, there exists an x and there exists a y such that x times y equals 0.
Yes.
Yes. Okay.
Could
So
you say that generally a there exists is mostly going to be true? Like,
I would never say something like that. No, I have no idea what the ratio is.
no idea? Okay.
No.
Like, what's a good example of
exists in case.
when it would be false.
Well, it's just
If every
There
variable.
exists an even prime number greater than 2.
Okay.
or case.
You can make up as infinitely many statements one way and infinitely many the other way, and
Yeah.
half of infinity is exactly infinity. So you can say half of them.
Is there more false statements than there are true statements?
If you can tell me if there's more positive integers or negative integers, I'll answer that question. Okay. Actually, that might be a lie. I don't know if you can create a correspondence like that. I'd have to think about it.
It's just too
It's a hard
nice.
question.
That'd be good.
The false ones might be. I don't know.
You can find a statement of all like false.
No, that's not the question. Some sort of way of lining up all the possible statements that you can generate, and then the ones that can be true or false. I think they're both going to be countable.
The way I imagine.
They both have to be countable.
The way
It would work.
I-
This is a huge detour. Counting infinite sets.
Sorry. Okay.
All right, we'll stick with this for now. But yeah, I think you could get they're both countably infinite. I think that's the correct answer. Okay, now let's come to these, and you tell me if they're true or false, I guess. So here's our predicate here. We turned it into a proposition. Is this true or false? First off, what is this saying?
Saying that for all x there exists a y such that x plus y.
Right. So say in plain English to a child,
There's always someone you can love.
everybody loves somebody is essentially what it says. Everyone loves someone. Everyone, for every person out there, there exists someone else such that they love them. Probably pretty close to true. Okay, what about this one? True or false?
One was false, I think.
For all x, there exists a y such that
False.
for all z,
None of it is.
yeah, so that one is false. What if I put there exists here?
That's what it just was.
No, that was
Oh,
what we just had.
and we put there exists here.
Yes, I would already.
For all x, there exists a y and there exists a z such that x plus y equals z plus 2.
It's true.
Yep, that one's now true.
That's true. Okay.
Pick any x you want.
10.
10. I can now find a y and z that satisfy this equation.
Yeah, you just do -10 and then.
I'll do 2 for that and 10 for that.
-2.
Yeah,
-2.
two and 10.
Very good.
I'll reuse your x there and always make that match that.
Yeah.
-2 or -10.
I see it.
Or you can think about it. Okay. Whatever.
Okay.
So, see how it's true. Okay. So, our predicate now is the is-a-miser predicate. So, someone who hoards up their wealth and won't spend it. Sleeps on smog.
Okay.
The dragon. All right. So, this is the is-a-miser predicate. What does this say?
There exists an x such that they're a miser.
Yeah, this is saying someone out there's a miser. There's a miser out there.
I guess that's a true statement.
Yeah, so most likely true. Okay, now we have the, what does this predicate say?
X is greater than 3.
So it's the is greater than 3 predicate.
For all x, no, that would be false if x is a number.
Now this is saying all x are greater than 3. Now you-
No, it's false.
Pointed out a good point that I should mention once, and then we're going to ignore it till we get there.
Yeah.
Which is, in the examples, you're often going to have to infer from context what are the objects are that we're talking about.
Yeah.
Eventually we will make that explicit, but in my examples, so in our theory, we're not justified in writing out sentences like this, but in our examples to help your intuition, we are justified. Because we're going to use material ahead in our examples. That's pretty normal. So it's understood that we're talking about numbers here.
So generally when we say for all x, if we were to be explicit, we're referring to everything in the universe, and then you have to apply where x is a number, or where x is, to then dwindle it down to a particular set, to then apply it to like a mathematical equation.
Kind of. It's understood, up here we're talking about objects in the universe. It's understood down here we're talking about numbers. I don't know if you want to say a number is an object in the universe,
Yeah, right, true.
but
In
so
reality.
we'll get to what we call our domain of interpretation.
Okay.
And we'll have our domain of interpretation. For now, we're just going to assume from context what's being talked about.
And a domain is really just kind of a way of
The set of all objects we're talking about.
and then it's just assumed.
So yeah, it's whatever the for all is talking about. In this case, for all meant numbers. In this case, for all meant, oh, that was numbers again. In this case, for all meant you could have said people, or you could have said objects in the universe. In this case, probably doesn't really matter.
Yeah, but so
Or no, it does matter. That's saying everything loves something. If we think love can only, well, how was that? It's not just people. We'll leave it at that.
yeah, but I guess a domain is always just for all x where x is a number or within this domain. Then we apply more where it's also in this, where it's also true in this case.
We will specify the domain that we're talking about. So when we're talking about algebra, our set is the real numbers.
I'm just
And
saying
that's what we're always talking about.
that you could always apply it logically by applying this filter where x is this. But
You can always scope it down more.
so
But when
start
you
out-
set up your system that your ultimate, remember this is language, we're talking about systems.
Okay.
We haven't gotten to talk about an axiomatic system yet. When we do, we will talk about our domain of interpretation that we care about. We're not there yet, specifying any domains. So it's like we gotta get used to how we work with them in systems before we can actually set up a system and be completely precise. Okay, so with that, let's symbolize now some sentences. Full-fledged, we have our complete grammar. We are now ready. Any English sentence I throw at you, you should be able to symbolize it now into this logical notation
It's amazing.
using our grammar. Okay, so all men are mortal, or all men are animals. All right, how do we symbolize this?
Whether exists a man, he's an animal, or for all.
There
men-
exists what?
I probably did it wrong.
No,
For all x. it
all
should
x.
be-
For all x,
Man predicate implies animal predicate.
No.
man to x predicate
That's what it
implies
And
animal
x.
to x predicate.
Yes.
And there we go, it's a proposition. Remember, this piece alone, just a predicate. Two ways to convert predicates to propositions. One is to give it a particular term that you're talking about, or terms, depending on how many it has. Two is to add a quantifier.
Yes.
Good? Let's try another one. All freshmen are intelligent.
All x. F x. Or no.
French
Implies
are intelligent.
y. Or I x. Sorry.
Implies IY.
I y. Sorry.
Just to make sure you know, there's nothing special about X's.
Right.
Doesn't change anything.
Yeah.
All right. Let's try
Sorry.
the next one. Not all freshmen are intelligent. And don't just put not and then for all. I should have written this top one, so while you're thinking about that, I gotta rewrite this a little bit more.
Doesn't that just mean you flip the case, the statement? You flip the application.
You tell me.
No, you change it to you negate it.
You do negate it, but doesn't that flip it?
How do you think? So it should be there exists a man or there exists a freshman that is not intelligent. That's how you did it. There
So this
Yeah,
is
so there
negating this.
exists.
So you
Yeah,
This-
so you do e.
Oh, it's not and.
Oh, you
it's
changed
and.
it to
is
x.
there exists an x.
There exists an X
Yes, such that.
such that
How are you gonna say that?
Fx.
Does not imply ix.
Implies not.
Implies not ix. Can you do that?
everything is perfectly legal here.
Sweet. Oh, sweet.
You have some predicate with its associated variable. So ultimately what it's going to return is a proposition. You're negating a proposition.
no,
and a
no,
proposition implies a proposition.
Doesn't it flip around? Or am I?
This says that there exists something such that if it's a freshman, then it's not intelligent.
Yeah.
Yes.
Right?
Yeah.
Now I'm going to rewrite, well, no, maybe I won't do that yet. But let's think about this for a second. Let's think about this piece of chalk. Is this piece of chalk a freshman?
No.
So if it's a freshman, it's not intelligent.
Wait, what?
Is this piece of chalk a freshman?
No.
No. So when I plug in this piece of chalk for x, this evaluates to false.
Oh.
And false implies anything is
True.
true.
So that's
So this piece of chalk, let's say that I exist in a universe
Uh-huh.
with all intelligent freshmen and this chalk.
Uh-huh.
Is it true that there exists something such that if it's a freshman, it's not intelligent?
Oh, I see.
Yes, this chalk.
But it's
So
not freshman.
it's not intelligent.
Maybe let's go through this exercise really quick. Alpha implies beta
Yep.
says the same thing as not alpha or beta.
Yep.
So what you wrote is equivalent to there exists X such that it is not a freshman, not freshman applies to X, or not intelligent applies to X. You're saying there's something out there that's either not a freshman or it's not intelligent.
It's also, it's an and statement. It's not, it's
Oh.
where they are not not fx and x, or I.
I think you have the right idea.
Or
You're just
not
saying
I. Yeah,
where
so-
they're a freshman and they're not intelligent. Yeah, you had the idea.
I see. So
There exists something out there that is a freshman and it's not intelligent.
Yeah, that makes total sense.
That's how we say some freshmen are,
are not all.
or
freshmen.
not all freshmen are intelligent. There exists something out there that is a freshman and it's not intelligent. If I were to say, prove all freshmen are not intelligent, what would you do? You go show me Jerry and you say, look it, here's a freshman and he's not intelligent.
Poor Jerry.
Poor Jerry.
Hopefully there's not a Jerry freshman.
There's technically another way to write this. It's not simplified, where you just do the negation, and then you say for all x implies f of x. Or sorry, for all x, there's f of x implies I of x.
We could have written this as, it is not the case that for all x, f of x implies not, or implies ix. That's the most straightforward way to say not all freshmen are intelligent. But I specifically said don't do that.
So that's cool because that we've just learned that if you apply the negation,
If
that
something's
you
not
switch.
there.
Yeah, you switch it in alternate.
Well,
So-
we see that in that particular case that happened.
Should
Will
be
that
true.
always happen?
Well, I'm sure.
You tell me.
Yeah, it does.
Does this always happen?
Yeah.
Guess we'll see.
It's a theorem.
Long drum roll. Okay. So we did that one. Let's try another one. No freshmen are intelligent.
It would be for all x. Not intelligent applies to it.
Yeah, not fx.
Not ix.
Not fx.
Wait, what?
Not I. X.
Oh,
you're
not
right.
ix.
It's-
No, because you
No,
This
no,
is
no,
saying
no, 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 'cause
Everything
that's-
is unintelligent.
You gotta say the
And
freshman.
it's-
You, me, we're all in trouble.
You gotta say the freshman.
And it's a freshman.
Yes.
So it'll be
So,
freshman applies and not intelligent. No.
so fx
Yeah, it should be fx and not ix.
and not.
Yeah, that's right.
Perfect. So everything is a freshman and not intelligent. You, me, and this Chuck.
Shoot.
Okay, that didn't work.
Okay. Okay, wait.
How do you do none?
It feels like it should be. So you're talking about the
Oh.
quantifier is everything, right? Because you're saying there's nothing there.
You tell me.
So the quantifier is everything. You're not-
So far, the quantifier is
It
everything.
should. So we're saying for everything that is a freshman, it implies that it is not intelligent.
There you go.
Oh, it implies it's
For all x,
That's-
if it's a freshman, then it's not intelligent.
Oh, that would-
No freshmen are intelligent. For all x, if freshman applies to x, then not intelligent applies to x.
Right.
That makes more
Or you
sense.
could say not fx or not ix.
Correct.
Oh yeah.
He just wants to think about it that way.
Yeah, that works.
But I don't know. To my mind, that's a more awkward way to think about it.
Yeah, it's
This is more natural to me than this.
Yeah,
it's useful
I
to
agree.
think about.
It's always useful to have that tool
I'm
in the
actually
back of your
surprised how
belt.
often I'm noticing that pattern in programming with not something or something. It's quite common.
Cool.
All right. Next, some freshmen are intelligent.
There exists a freshman such that fx and ix.
And oh yeah.
I would say an
Is that
implication
it?
again. It's another implication.
It's an implication again.
So it's fx implies ix.
It's saying there exists something such that if it's a freshman, it's intelligent.
Oh yeah, it is.
No, it's not.
Oh.
What?
See if I can get you guys to switch. What are we saying by some freshmen are intelligent? We're saying there's something in this universe
That is a freshman.
that is both a freshman and intelligent.
Right.
Again, imagine we put the implies here, because this is one of the easiest mistakes you can make encoding these sentences. Putting the implies when you mean and putting the and when you mean implies. Think about the implies, and then use what you have up there. there exists X such that it's not a freshman or it is intelligent. In this case, this piece of chalk satisfies it. This is something that either is not a freshman or is intelligent. Because it satisfies this part.
That's true.
Or up here, the way to think about it is it makes this implication vacuously true.
Right. Right.
So this is something such that if it's a freshman, it's intelligent. So that's why we don't have the implies, we have the and.
It's a lot stronger. Seems like, I don't know.
And is, yeah, I get what you mean. And is a strong statement. Adam is not married to anyone. Put my own flair on the name, you know? Alright, so how do we write this? Get a little bit more tricky.
There exists an X such that
His name's Adam.
Adam predicate
X is Adam.
There exists an X such that
No, I think
having
it
the
should
name
exist.
Adam applies to X.
Yes, I
Okay.
That's one way
That works.
Alright.
Does it?
And, I don't know. I think it is.
Yeah, I think it is.
Yeah,
And-
his name is X's name is Adam.
I think-
What is Adam?
And
Okay, go ahead.
wait.
And,
Oh,
No,
there
Adam is a
X,
specific.
there
It's a
exists.
specific person. Why are we making him a general?
Alright, Adam is
He's a
just a
term.
constant.
Guys, he's not.
So we'll use, yeah, he's not a predicate.
He's not a predicate.
person, guys. He's a term. Alright, so we'll use little a to signify Adam. Little a now means Adam.
Adam.
So,
Adam.
I think it's still all X, right?
For all X.
For all X.
For all like
No,
Yeah.
not.
No,
all.
we
Not
do
all.
for all over a variable. We don't say for all Adams. We don't say for all numbers 2. For all
He's
X.
not married to anyone. So, it would be
What if we
M,
use
big
and?
M for married, right?
you're not. So it's gonna be not.
Not married
There's two
is
terms.
a little a and I don't know, Z for anyone or something. Or no, because we have to.
Is X
X.
referring to anyone in this
Yeah,
case?
that's
X is
for
referred
all.
to.
For all X,
Yeah.
not married applies to Adam and X.
Yes.
Weird.
Or writing it a little bit more natural, we just said for all X, it is not the case that Adam is married to X. That notation would have also been fine. Using our infix notation, since it's a
Relational.
relation.
It's a relation.
It's a relation.
There are
A two-term predicate is called a relation.
Relational predicate.
Just a relation.
It's
It's a type of predicate. We don't say you're a human animal. Say you're a human. It's a type of animal.
I might say that.
Why does it not go before the A instead of like in your second one? Why is it not A not MX instead of not A MX?
If I wanted to say it is not the case that 3 is less than 5, I would write like that.
You wouldn't write 3 as.
And it's understand that you apply the not to the proposition.
Can't you just distribute the not and then just say 3 in the right, like a dash through that and say 5?
So that's some common notation, but we haven't developed that notation for a line, slanted line through M means the negation of
So
M.
you put it through, you put at the very beginning of the predicate.
Yes, the negation comes before your proposition. 3 is less than 5 is a proposition. If you're going to negate that, you put the negation in front of the proposition.
Okay.
Yes. Okay.
Good?
Parentheses are nice.
Yeah, it's... With the negation there, this is probably a nicer way to write it. But both of those would have been acceptable. Okay, let's try the next one. Some freshmen date Elizabeth.
There exist X such that X is fresh.
Such a freshman applies to X.
Freshman applies to X, and dating
applies to
applies to X and Elizabeth.
Perfect, that works.
Nice.
Where D is dates Elizabeth predicate.
Yes.
Is dates, and then that applies to X and Elizabeth.
Right.
Yes.
That's different
D
than,
stands for dates.
that's different than the date Elizabeth predicate, right?
D
Then
stands
the
for
dates
blank.
Elizabeth property.
Yeah.
So
D stands for
if
blank dates.
we could have done that. We are assuming from context that you are understanding what D means, and I'm not explicitly writing what D is up here. But yes, we could have done the dates Elizabeth, and we could have said we're going to define D as the
Date Elizabeth.
blank, using X for a blank, dates Elizabeth, predicate, but property in this case, and then we could have done it that way. But this is the most natural way to do it. Yeah, explicitly write out all the terms that showed up.
And Elizabeth is just a term here.
Yeah, Elizabeth is a term, Elizabeth is a constant. X is a term, X is a variable. Elizabeth is a term, Elizabeth is constant. All your terms are either variables or constants.
Yes.
So when we say there exists an X, we mean there could be more than one X,
Yes.
yeah, at least one.
There exists always means at least one.
So multiple freshmen could be dating Elizabeth.
Yes.
Or one freshman could be dating.
The whole freshman class could be dating Elizabeth.
Not dating, they date. That's.
Same thing.
Same thing.
Dates Elizabeth.
Yeah.
Dates,
Does it imply all
dating.
the same time?
Well, yeah, I would. Well,
Dated.
We're not going to worry about that.
Yeah.
Okay. However you want to interpret it, we got enough of the structure there that I'm satisfied. Okay. So there we go, giving you a bunch of intuition for these symbols and how to use these symbols. I have yet to define what these symbols mean.
Oh,
So now we're going to define it.
okay.
Okay? So first we're going to define the universal quantifier, and then we'll define the existential quantifier in terms of the universal quantifier, and then we'll prove a property you were already hinting at. Okay, so let P be any predicate. So what's P? Is something such that if you give it some term, it spits out a proposition. It's a proposition value function. Could be something like is blue. Good?
Okay.
Then, for all x, P of x, now, is a proposition. This is something that is either true or false. And how do you determine if it's true or false? So then, this is a proposition, and it's true if and only if P, our predicate here, is true independent of x. Concrete example.
Exists.
Let's look at this.
Sorry.
Huh?
Sorry, predicate exists. I was just thinking of an example.
Okay, so here's a concrete example. Notice x is greater than or equal to x is always true, independent of your choice of x. So since our predicate here is true, independent of our choice of x, then for all x, x is greater than or equal to x is true. That is a true a true proposition.
Kind of like a tautology.
A little bit.
Kind of. A tautology you could do the truth table for. This isn't something you can do a truth table for, but it's still true independent of your choice of x.
Right.
Versus this one. For all x, x is greater than 3. X is greater than 3 is a predicate, but it is not true independent of your choice of x. And so this whole proposition evaluates to false.
Okay.
So let P be any predicate, then for all x, P of x is a proposition and is true if and only if P, our predicate, is true independent of our choice of x. Otherwise, we call it false. That makes sense? That was pretty intuitive. Next one, not so intuitive. Let P be any predicate. We're now going to define what the existential quantifier means. There exists an x such that P of x. Here's common notation. I am defining something new, and I am defining it to be logically equivalent to this thing.
Yeah.
The colon is on the side of that has the new terms I'm defining.
Yeah.
So that's what that colon there means. It's saying, hey, the thing on the left-hand side has a term that hasn't been defined yet, and everything on the right-hand side should only be terms that we've already defined, and we know what they are. We've already defined negation, we've already defined the for all x, we've already defined negation, we've already defined a predicate, we've already defined, these are all symbols that we know. Here's where our new symbol is. Okay, so now I'm saying there exists an x such that P of x is defined to mean that it is not the case that for all x, not P of x. Now again, we know that this is a proposition, How do I know this is a proposition?
Because
Here's a predicate. Here's for all, a universal quantifier in front of a one-term predicate. According to this, that's a proposition, and negating a proposition is just proposition. So the thing over here has to be a proposition, something we can call true or false. Because I'm saying it is this proposition. That's what it means. Now let's get intuition for what this is saying. I'm going to choose my predicate to be is white, and we'll pretend the set of everything we're talking about in swans. So let's pretend that this says, there exists a white swan. That is logically equivalent to saying, it is not the case that all swans are not white. There exists a white swan says the same thing as it is not the case that all swans are not white.
Yeah.
There is a white swan. Well, that's connecting your intuition to the definition. There exists an x such that p of x says the same thing as it is not the case that for all x we don't have p of x. If there exists an x such that p of x, it is not the case that all x give us not p of x.
What's the term for this? I know it's not negation. It's the
Kind of think.
Just the definition for the existential quantifier.
You think like Converse or something?
yeah, something like that.
Yeah.
You guys are on the same page somehow.
I get what you're saying.
I don't know what the page is.
There's something that
Yeah, I know what you're going at.
there's a term for this that I don't remember.
Okay. And then I didn't know if we need to do this or not. I don't know if you've seen that symbol or not. There exists with the exclamation point after it.
It's not.
Okay. We don't need to worry about it. I don't know. Do you guys care?
Gotta
Yes.
do.
Yeah.
Okay. We can do it. This means there exists a unique x. There exists one and only one x. Such that p of x.
So it makes the sum definitely one.
One and only one.
One and only one. Interesting.
So that's what that notation means. And here's its definition.
I was just saying there exists one. I guess it can imply.
We have to define it in terms of symbols that we already have. Now, technically, we can't define this yet because it has to use the equal sign, and we haven't introduced that to our logic yet. But I'll give you the definition. Here's what it says. When we say there exists a unique x, such that p of x, we're saying that there exists an x that satisfies p of x. So there is something out there that satisfies p of x. And for all y, if y satisfies p, y must have been x, because x is the only thing that satisfies p.
Okay.
So there exists something out there called x that satisfies p. And for anything else, if it satisfies p, it must have been x.
Do we use
That makes sense.
that a lot in math?
It can be useful in some things, like common way that you see is proving that there's a unique multiplicative identity, there's a unique additive. Proving unique identity elements is a common way that that notation comes up.
Okay.
That's the first thing that comes to mind.
Who comes up with these?
We did, right now. Look at us go.
Must have took them forever to kind of think through, unless they're just like extremely brilliant.
Or just the word.
Well, I'm actually not sure if this is the exact definition that they give,
Wow.
but it's a logically equivalent one. I mean,
Yeah.
that's what it says.
Someone had to say, okay, these are the rules I have to work with. I need to find this one. I have to come up with something that would describe it. And I don't know.
Think about how people would feel about looking over your cup. Yeah, someone must have just sat down for hours and just thought about this and wrote it out.
It's true. Yeah.
Let's see. That doesn't quite get the whole thing. Shoot. See if I can. A little bit further back.
There's a perfect example, because nothing that you create, you have created already, unless you're an idiot.
Nothing you created already.
You don't create anything you've already created, is what he's saying.
Oh, that's what you're saying.
That's like duplicate code.
Right.
Wow.
Don't duplicate your work. Okay. Since we're over here, I'm going to rewrite this definition. We'll scribble that up here for a second just so it's on camera. So it was, there exists x such that p of x is defined to be, it is not the case that for all x, not p of x. Right?
Yes.
Okay. So now we're going to prove our first theorem. Here's the way that everyone thinks about negating this thing. So let's say that you have for all x p of x and you want to negate it. I want to negate a statement like all swans are white. What does it mean to negate all swans are white? It means to say that there exists something out there, there exists a swan that's not white. That's what it means to negate all swans are white. Now the way that everyone thinks about this, about how to negate these quantifiers, is you bring the negation inside and apply it to your predicate, and you swap your quantifier. You replace it for all with the there exists. Similarly, if I want to negate there exists of white swan, that's the same thing as saying all swans are not white. So when I want to negate an existential quantifier, I can distribute the negation into the predicate and swap my quantifier from a for all to a there exists or from a there exists to a not. Now I may quickly prove that, but that's what we're doing, what we're proving, and it's a very useful way to think about it. It's the way I always personally think about it. That's what I do in my head when we think about negating universals. So let's prove this. I'm going to start with this thing over here and show that it's the same as this. You with me? So we're going to start with there exists x such that not p of x. And we're just going to look at its definition. There exists x, some predicate about x, means not for all, not that predicate. So by definition, this is logically equivalent to, I put a not, whatever I had here, put a not, then I put up for all, and then I negate whatever that predicate was. So I negate whatever my predicate was, and my predicate was the not px.
Okay.
That's just using the definition. Now we already proved that not is the same thing as just that thing. And so this is the same thing as not for all x p of x. And we're done. Quick little scratch proof. So I showed that this is logically equivalent to that. That's what we were after.
Right.
Yes.
I was showing that is logically equivalent to that. That's what we were after. Apply the definition, double negation.
QED, yes.
There we go. Next one. I'm going to show this is logically equivalent to that. So not there exists x such that p of x. Now I'm going to look at the definition of this part and plug it in. What is the definition of there exists x p of x? So this is logically equivalent to, keep this sign, and now what is the definition of this thing? The definition of that is not for all x, not p of x. This is the definition of that. Just replace it exactly with this definition.
Yes. So not that applies.
And so not goes out. The negation of some proposition is just that proposition. And so this is just for all x, not p of x. Pretty straightforward, quick little proofs, but useful ones.
Those very useful ones.
Yeah, so when you negate an existential quantifier, you can distribute it to the inside and plot your quantifier. And it turns out that this works, distributing it over multiple quantifiers. We don't bother proving that, but it does. Okay. Atomic formula. What is an atomic formula? It's like the smallest formulas we can make. It's going to be a predicate together with the appropriate number of terms. Maybe constants, maybe variables, but the appropriate number of terms. So not necessarily a proposition, but it could be a proposition. A proposition could be an atomic formula. A proposition may not be an atomic formula. So an atomic formula is a predicate together with the right number of terms, maybe constants, maybe variables. Okay, so example. If R is the is red predicate, and A is this apple, then it's saying this apple is red. That is a predicate together with the appropriate number of terms. That is an atomic formula. In that case, it happens to also be a proposition. That's just a predicate together with the appropriate number of terms.
To be a proposition, is what you're saying.
to be an atomic formula
Right.
is just a predicate together with the right number of terms.
So that it can
Maybe constants. It could be a proposition if you give it a constant. It's not a proposition if you give it a variable. So this says x is blue where x is some variable. This atomic formula,
But it's not a proposition.
but it's not a proposition.
That makes sense.
X is greater than 3. Atomic formula, not a proposition.
Yeah.
Jack loves Jill.
Uh,
Is that an atomic formula?
yes.
How many predicates does it have?
No.
Loves as one.
Or,
1.
yeah.
It's one predicate together with the appropriate number of terms.
Right. So it is.
One predicate together with the appropriate number of terms.
Okay.
Let me show you a non-atomic formula. I put an and here. So now we have 2 predicates.
Why is that not atomic?
What makes that not? Does it
An atomic formula is a single predicate. It's atomic. It's like the smallest formulas we can make.
Right.
A single predicate
Because I don't
Yes.
know why I don't make that.
together with the right number of terms.
Yeah.
Let me give you another example of not an atomic formula.
That's wrong number of terms.
Jack loves.
Yeah.
Finish it. You can put a variable there and say Jack loves X. Okay, that's fine. Or you could put Jill there. Okay, that's fine. But you got to give it all its terms.
How do we?
You can't leave it hanging.
What if it had more terms? Okay.
Then the appropriate number. So Jack loves Jill. Bob. But now it's just nonsense.
Right. How do we?
Not an atomic formula because that's not the appropriate number of terms. Loves was a 2-term predicate and we tried shoving 3 in there and we broke it.
How do we define the right number of terms?
Yes.
It's dictated by the predicate.
How do we-
Right.
Yeah, but we're trying
When
to.
you write out a predicate explicitly, you specify the terms it takes.
Is it because this predicate doesn't have any of the potential connectives?
Potential connectives could show up inside of a predicate.
Well, then how do we know that it's not 2 predicates inside that predicate?
Because the way that this is explicitly written out is with 2 predicates. I could have secretly written W as a predicate, and W is the predicate is equal to the is blue and is greater than 3, and now I could say W applies to Y, whatever,
And is that atomic?
and now that would be atomic.
Okay.
It's just a single predicate
Yeah.
together with the appropriate number of terms.
Okay.
And if you secretly define some predicate in terms of other predicates, okay, then that's what you did. But in now the new language you constructed, you made so that one of your basic units, one of your basic predicates, is W.
Oh, that basically means I get to decide what atomic formulas are.
In your system. You get to choose your system however you want, and then the atomic formulas are the atomic formulas. Each predicate you define with the appropriate number of terms is now an atomic formula in that system.
Yeah.
Okay, so it's a pretty straightforward concept once you get it.
So what's the official formula?
Yeah.
If we're going to define formula, we just need atomic formulas to define formulas.
Weird.
So we good with atomic formula?
Yeah.
All right, now we get the formula. It's kind of a recursive definition. What is a formula? 1. Every atomic formula is a formula. Okay? So you're wondering, do I have a formula? First thing to check, is it an atomic formula? Then yes, you have a formula. Okay, maybe it was an atomic formula. Maybe it was something like this. Is this still a formula?
Yes.
Next thing we check, if R and S are formulas, maybe atomic formulas, like they are in this case. Here's our R, here's our S. If R and S are formulas, so are, not R, the negation of R. If R is a formula, the negation of R is a formula. If R and S are formulas, R and S is a formula. If R and S are formulas, R or S is a formula. If R and S are formulas, R implies S is a formula. And R is logically equivalent to S is a formula.
So is not S, right?
So it's not S, but that's covered by not R. For any formula R, not R is also a formula.
Yeah.
Yeah.
So I can take atomic formulas, I can AND them together. I could have taken that atomic formula and negated it, and it still would have been an atomic formula. I could have said this implies this, and this would have been a formula. Now that that's a formula, I can take that and I can AND it together with Jack loves Jill. And this whole thing now is a formula. Because I ANDed together two formulas, which is legal. And here, I was saying one formula implies another, which is legal. And here, atomic formula, atomic formula, atomic formula. So ultimately, it's going to reduce to atomic formulas, and you build it up out of atomic formulas and combine them together. So I start with atomic formulas. One of the things I can do is I can apply all my logical operators, all my sentential connectives to those formulas to construct new formulas. That's one thing I can do. Next thing is, if R is a formula and X is a variable, then for all X, R is a formula, and there exists X such that R is also a formula. So, if I have, give us some scribble space here, if I have X is greater than 3 is a formula, right? That's a formula. I can now say, for all X, X is greater than 3. Still a formula.
Is that an atomic formula?
No.
Maybe.
No. What is an atomic formula? A single predicate together with the appropriate number of terms. No quantifiers can ever show up in an atomic formula.
Makes sense.
No sentential connectives can show up in an atomic formula.
But
The atomic formula is just a predicate together with the appropriate number of terms. One predicate. You'll have one capital letter, and then your lowercase letters.
and the predicates could have quantifiers.
The predicates could be defined in terms of other symbols. But when you write it out on the board, you better be able to write it as a single symbol, single capital letter, and then the appropriate number of lowercase letters.
Fair enough.
Okay.
So, what really is a formula then? Like, what are we describing?
And then no expression is a formula otherwise. So here's our formulas.
What does that do for us?
It tells us what a formula is.
What will not be a formula?
Intuitionally, what is a formula?
Intuition, it's almost the structures we care about. We're going to care about particular types of formulas, the ones that are behaving nicely. But it's a way of saying we don't. So far we talked about the symbols that we use in our language, in the grammar that we use, right? And we don't want to go willy-nilly using these symbols in any random order that we want. There's a right order to it. And the formulas are ensuring that everything is ordered correctly. We are intuitively just going off of how we know to read these things and writing this out. And that's us applying our own reasoning to it. But now look at something like this. Is this a formula?
No. No.
What?
I guess so.
No.
Is this a formula?
Because
X
implies
equals Y
or.
implies
Or doesn't make sense, it doesn't have enough terms.
No.
Implies or is
No,
not.
it isn't.
Because I don't even know.
And
Okay,
does
so that's
all
kinda weird.
else implies
And now if we get rid of that, we're now okay, right?
or
I don't know how to
No,
do
no,
that
no.
quality. What's equality?
all x does not equal.
Well, pretend that equals is equal predicate. So we can replace that with capital E if you want.
Equals is if and if.
But we can go like that if you want.
It's logically cool.
X equals Y.
For all x, if and only
Y
if
is
there exists x, doesn't make
No,
sense either.
if and only if is logically equivalent, is not equals.
no. That should still be. it should
And
still
the only question is not is this true or false or anything like that.
be- Yeah. Yeah.
The only question is this a formula? That's all we're asking. Is it a formula? Does it follow the rules stated above?
Yes, I guess so. I was gonna say yes.
So first off, how many atomic formulas are in there?
1, 2,
1.
2.
There's
No,
two.
1. Wait.
3.
What is an atomic formula?
So the predicate together with the right number of terms.
How many predicates are in this?
I'm seeing.
Oh, there are no predicates, so it can't
There's
be
one
a-
predicate.
What do you mean? AX and EX, aren't those predicates?
Those are quantifiers.
Son of a.
Every single symbol falls into one of these 5 categories.
Right.
It's not a predicate, it's a quantifier.
It's a
yeah.
quantifier. So there's one predicate. It's the equals predicate.
Oh,
It's the
shoot.
equals one. Yes,
There's
but
one atomic
I'm
predicate.
talking
It's
about
the
the
equals predicate.
Oh, I didn't even look. I saw those E's and I thought they were just symbols for predicates.
Okay, those are not names of predicates.
I
Good.
have dyslexia, don't even.
Those are quantifiers. Okay, so restart. How many predicates are in this?
There's one.
One.
One atomic predicate.
There's one predicate.
Yeah.
Okay.
And it has to be atomic.
one.
No,
Is that
a
not?
predicate isn't atomic.
Or-
There's one atomic formula, and that's right here.
You're right. Sorry.
So far we know for sure that this piece is a formula. An atomic formula, so a formula.
Mm-hmm.
Okay. Now, I can only apply implies to two formulas and still have to be a formula.
So is that?
So this other thing over here would have to be a formula.
Right.
Is this a
It has
formula?
No predicate.
There's no predicate, so it can't be.
It can't be. There's no way for me to generate this string following this procedure. So this procedure gives me my rules for how I can generate these formulas. Kind of. That's one way to think about it. But if it's a formula, we should be able to generate it starting with some atomic formulas and applying this rule as many times as we want and this rule as many times as we want to generate whatever we want. And that will be a formula. And so you see how this procedure is stopping us from generating nonsense like this. So far, that's one of the things that formula is doing so far, is it's adding some proper structure to the way we can put these symbols together. So we don't try doing stuff like this, which is just pure nonsense.
Yeah.
Yes.
Yeah. Okay.
The or was there too.
Right, before we also had an or there, because, yeah, why not?
So you can. So that might be an expression, just not a formula.
Yeah, that's some expression. It's not a formula.
And we only are concerned with formulas.
Yes.
Right, we're going to be
Formulas help us.
mostly, everything we're going to be concerned with is formulas. And a large part of what we're going to be concerned with is certain types of formulas. So we're still not, in general, just interested in any formula. And we're going to restrict it down. We're going to be largely interested in what we call sentences. We're almost there. Before we do that, we have to talk about the scope of a quantifier. The scope of a quantifier is the quantifier together with the smallest formula following it, immediately following it. Let's give a concrete example. You could have almost guessed what was meant by the scope if I just asked you rather than that definition. So up here, every time you see a quantifier, it has an associated scope. It has what it applies to. So the scope of a quantifier starts at the quantifier, and it ends once we have underlying a formula coming after it. So the scope of this quantifier is from here to there. There's the whole scope. This quantifier does not apply to this. This was not in its scope.
Unless there's parentheses, right?
Well, is this a formula? M of x, is that a formula?
Yeah.
Yeah, it's an atomic formula. So what is the scope of a quantifier? The scope of a quantifier is the quantifier together with the smallest formula following it.
Doesn't the smallest formula just mean an atomic?
The atomic formula.
No. Next one. Let's look at the scope of the there exists x.
What's okay? So
There exists x. Now that's the smallest formula following it, right?
No. Because the parentheses, you didn't finish. that.
Because of parentheses. This is not a valid formula in our notation. X greater than y with that parenthesis there. That's not a formula. That's nonsense. If there were another parenthesis there, okay, now we'd be good. That's something we can generate from our sentences.
okay. Oh, okay. I see.
But that alone, that is not a formula.
Weird.
Makes sense.
Okay, so the scope of this quantifier keeps going. Nope, we don't have a full formula. Nope, 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 nope. Got it.
Wait, so
Well, no, technically. Oh no, you didn't because
Oh, no, you didn't.
yeah.
There was never a point. This is the smallest formula immediately following the there exists.
I was just looking at the other parentheses that there were, but they were closing the other.
And so notice that we have a quantifier inside the scope of another quantifier. Perfectly legal. If we were looking at this quantifier, it would be the entire formula.
Is that why that didn't work?
What did it work?
This didn't work for lots of reasons. There's lots of bad things going on. We could never get even this piece of it by itself.
Yeah.
It's because it doesn't apply to
All
the
x
scope.
equals some x.
If you're going to do a logical equivalence, it has to apply between two formulas. So this would have to be a formula.
It's not.
And for all x isn't a formula. For all x, we can only introduce in front of some formula with parentheses around it if we want.
If we want.
Wait, hold on. 'Cause what about all y?
So the scope of this
Uh-huh.
is everything,
Okay.
including the scope of this.
Yes, that makes sense.
Oh, okay. So we start in and we work our way out.
You pick your quantifier that you're talking about,
Uh-huh.
and then continue going until you've found the smallest formula that comes after.
So what if I pick a all y?
So if you pick for all y, now what is the smallest formula that comes after for all y? And the smallest formula that comes after is this whole thing.
Interesting. All right.
Try cutting it down shorter. If I tried stopping right there, right there, right there, right there, right there, I get something that's not a formula.
That part I understand.
So we have to go all the way, and this is the smallest formula coming after for all y. And so it would be the whole thing. All right, let's try another one. This time we'll do the for all y. What's the scope on this for all y?
That means
No.
everything after that.
Everything after it?
Yeah.
Yes.
Yes.
Yeah.
Why do we have to include the and?
It's in the parentheses.
It's in the parentheses.
In the brackets.
It's in the brackets.
Brackets,
Predicate.
okay.
Sure.
Brackets are parentheses, I think.
Well,
Same thing.
Same thing.
they're like
Same.
bigger.
They are identical in this course. It is only for the sake of eye candy that we do the square brackets to help us keep track of which goes to which. But yeah, they're just parentheses. So they come under the parentheses when I say every single symbol here shows up in one of those categories over there. One of those 5 categories. Always in front. Okay, and now the last one, starting with the for all y. How far do we go?
To the 0.
To
To after the 0, to that last parenthesis.
Yep.
And so parentheses make a huge difference.
Why
These
is
are
there a bracket?
identical. In one case, we have the square brackets. In the other case, we got rid of them.
What? Doesn't there need to be another bracket?
You put a square bracket on the end of that one. Is that meant to be there?
Nope. And that is because I messed up.
Okay, then that, yeah, we're good.
There we go. The whole thing is a formula, and the scope of this variable is that.
Sweet.
And it doesn't matter if the y's showed up again over here or they didn't. They wouldn't show up in that scope. That scope is that scope.
Okay.
Good?
Yes.
Okay. So now, a particular occurrence of a variable is free if and only if it does not occur in the scope of a quantifier of the same variable. Up here, so here's our quantifier, right? Look at this x. Does this x occur in the scope of a quantifier using the same variable?
Yeah.
Yes. Look at this x. Does this x occur in the scope of a quantifier using the same variable? So this is a free occurrence of x. This is not a free occurrence of x. A not free occurrence of x we call a bound occurrence. So every occurrence of a variable is either free, meaning it doesn't fall inside the scope of an appropriate quantifier, or bound, meaning it's bound by some quantifier.
Why does that
Isn't that switched on the top then?
Oh, which way did I say it? Let me say it again. This x is free.
Yeah, you had it.
I said it backwards. Sorry. Good. That x is bound. This x is free. It's free if it does not occur in the scope of a quantifier.
What does that mean? No.
Oh, so a quantifier isn't in its scope. Or
Does this x occur in the scope of a quantifier using the same variable?
Look at
Yes.
that part.
So it is not free. Or in other words, it's bound. Does this one occur in the scope of some quantifier?
No.
So it's free.
I'm just curious.
Bound occurrence, free occurrence. We're going to go over all these variables to say if they're bound or free.
I just don't know what it means to be free.
Well,
not bound.
I get that it's not, why is it?
It's not in some quantifier's scope.
Is it even a valid, true fault, like, predicate?
We'll answer your question. I get what your question is, and you're thinking right. Right now you're thinking along the lines of aren't free variables kind of useless? Yes. Okay. Next one. Each variable, is it bound or free? Is this x bound or free?
Yes.
That one's bound.
Bound. It's bound by that quantifier. Is this variable bound or free?
What's bound?
It's bound by that quantifier.
Yes, yes.
And that's a quantifier, so that's not the variable.
Okay.
Is that variable bound or free?
Bound.
Bound by that quantifier, and that one is bound by that quantifier. So in that case, all our variables were bound.
Yes.
Next one. There exists an x for all y. Bound or free? Bound. Bound. Those are variables, or quantifiers. Bound, 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 bound. Okay, bunch of bounds. Here, both bound. Here, bound, bound. So, only had one instance of something being free, everything else was bound. Because there was some quantifier applying to it.
But if there's a variable.
Let me try one more, just to make sure we don't get confused by this. For all x, there exists a y such that x plus y equals z.
Z is not, it's free. Z is free.
X is bound, y is bound, z is free. Good. And that's what we meant, a quantifier of the same variable. That's what the of the same variable meant on the quantifier. Because each quantifier has its associated variable. Good? Okay. Now, this was for a single occurrence of the variable. So we were calling each occurrence of x and each occurrence of y and each occurrence of z bound or free. If in the entire formula a variable has a single free occurrence, we call it a free variable. And if it has a single bounded occurrence, we call it a bounded variable. A variable can be both free and bounded. In this top line, x is a free variable and x is a bounded variable. Because it shows up free in the formula right here, and it shows up bounded in the formula right here. Down on this line, x is only a bounded variable. Every time it shows up, it's bounded. So, a variable is free provided it has a single free occurrence. And a variable is bounded provided it has a single bounded occurrence. So a variable can be both free and bounded. That means it has at least one free occurrence and it has at least one bounded occurrence. That's what it means to say it's free or bounded in an entire formula.
We still are referring to the same thing.
Same thing. It's just a way of talking about a variable in a whole formula now rather than just talking about one particular case. Okay. So now, here's our definition of a sentence. A sentence is a formula with no free variables. They're all bounded. And so, these formulas with no free variables, it turns out, are going to be propositions, things you can call true or false. And you're right on the money. You were thinking you can't call this true or false. And that is correct.
What about the second example you gave up there?
You cannot call this true or false.
I can't say that in a second.
Strictly speaking, this could be a large way. If I say L, this is like L of Z is equal to this thing. This right here could be a really messy way of writing a property, a one-term predicate.
But
It's the, for every number there exists another number such that they sum together to be that number property. It's an ugly one, a useless one, but that could be a way of just expressing some property, some proposition, or some predicate.
so how is a sentence in logic different than a sentence in English?
Okay, so, bit of subtlety now. Up till now, we've basically been thinking about English sentences as sentences. Strictly speaking, what we care about is we take some English sentence and we're going to encode it into a logical sentence, a sentence in our grammar. Our grammar generates sentences that we care about. So if you go through these generation rules in such a way that you have no free variables, you have now generated what we call a sentence.
And we can really generate any sentence with just these.
Encode it.
Encode it.
If we're going to get some English sentence's logical structure, what that means is, what is the sentence using our grammar that encodes this English sentence? That's what it means by talking about that sentence's logical structure.
We can encode any sentence.
To the extent that the sentence has logical structure is to the extent that we can encode it into these symbols.
Right.
If we can't, it doesn't have logical structure.
Maybe it'll be like a question.
Because that's what's meant by logical structure.
You're saying question.
Yeah, so like a English sentence that is not a statement would hold logical structure.
So it has to be statements.
But even then, not all statements, right? All men are mortal, it turns out, or sorry, not all men are mortal. Just saying men are mortal, it turns out that's really just a predicate.
Right, okay. But my thing is,
You could encode it.
all,
It just wouldn't turn out to be a sentence.
It would be a sentence as we use sentence,
As defined here.
all,
as defined here. Our encoding results in a predicate.
what about, so English sentences that are not statements do not encode logic in them.
So if an English sentence is not a statement, it for sure does not have a corresponding logical proposition, a corresponding logical sentence in this sentence.
Right.
But just because it is a sentence in English, or a statement in English, according to the English grammar, does not mean that it is a sentence when we look at its logical structure.
Right. So,
So here's sentences in English. Here's the ones whose encoding logically is a sentence. And it's a subset of it.
Is there a sentence that you can think of that would have a free variable in English, for example?
That's what men are mortal says. It's saying
Yeah, so
man applies to X, or men are animals, so that we don't do double N. Free variable, free variable.
it's true. It's safe for all that.
Okay, yeah.
so that's a sentence in English, but it's not a sentence in logic.
Correct. There's an example.
That
So a
makes
sentence
sense.
in logic is going to have a true or false encoding.
Perfect. Now in terms of logic, here is propositions. All propositions. Here are sentences as we mean them now in this class, as just defined. All our sentences will be propositions. Things you can call true or false.
So you won't have any. Okay, I see.
Cool.
So every sentence will be a proposition.
Yes.
Every sentence in this class is a proposition,
So what-
meaning sentence as we just defined it.
So what structure does a sentence give us that we don't already get with proposition?
A proposition is a lot more abstract. It's anything you can call true or false. And it doesn't have to have all this structure that we build up for logic here. In propositional logic, we don't even have the notion of a sentence, strictly speaking. Because a sentence is generated from these formulas, and we don't have these formulas. Because we don't have predicates. So it's, let's nail it down. I don't know.
Okay.
It's more abstract. It's just propositions. And now we're talking about propositions that come with this structure in it that we call sentence. Okay. But as I said, we'll pretty much use them interchangeably. That's a bit subtle.
If I was to try to distinguish the two in a conversation, would it be a logical sentence versus just a sentence?
So a lot of the times, a lot of confusion people have in regular conversation is because technically what they're talking about is a predicate, and it is not a proposition. And so it's open to, if you're going to pretend it is a proposition, it's open to multiple interpretations. When I say men play golf, what am I saying? Am I saying some men play golf, or am I saying all men play golf? Common example that I bring up is the ends justify the means. Now that's a perfectly fine question. Do the ends justify the means? That is a perfectly, did I do something weird?
You didn't do this.
You didn't like the question.
You didn't.
Right, the statement. The ends justify the means. The question is the statement true or false?
Yeah.
But the ends justify the means. There's a common topic of conversation that you might have amongst some kids, okay? But when I see a philosopher write that as a question or write that as a statement, I want to throw something at him. Because strictly speaking, this isn't saying anything. It's just a two-term predicate. And you either have to give me a particular ends and a particular means for me to call this true or false,
Or you have to
and say something like, buying a house justifies me robbing a bank. Okay, now you're giving me particular instances of ends and means.
Or you put a quantifier.
Or you need to add two quantifiers. And so there's four different ways you can interpret this sentence. Are you saying for all ends and for all means, the ends justify the means? Are you saying for all ends there exist means, such that the ends justify the means? Are you saying there exist an ends such that for all means, the ends justify the means? Or there exist an ends and there exist means, such that the ends justify the means? And those are all four perfectly valid ways of interpreting that. And if you choose one interpretation and I choose another interpretation, we can argue till we're blue in the face. Because we're not talking about the same thing. And so a lot of disagreements in day-to-day language, day-to-day conversation, can come from simply you're talking about these types of things as though they're propositions. When really someone says, do the ends justify the means? The correct answer is, that's an invalid question. Question with a false premise baked in. You're presupposing that the ends justify the means is a proposition. You know false questions? You used to ask them when you were a kid all the time? Does your mom know you wet the bed? No. Then you should go tell her. Question with the false premise baked in.
Yeah.
So if you say yes, you're in trouble. If you say no, you're in trouble.
Yeah. It really does allow a lot of
Ambiguity.
being right, no matter, yeah.
So it can clear up a lot simply to say, let's write out exactly what we're talking about. And let's write out the logical structure of this statement. What do you mean by this? And now, if you were to write it out with all its quantifiers, now it's completely unequivocal to the extent that it can be what exactly you're saying. And now we can do a logical analysis of what exactly you're saying. So that's extremely useful.
So how do I just communicate if I was to be confronted with such a statement? How would I,
Did you repeat that somebody?
that I'm like,
Well, the first thing you would ask is, what do you mean? So kids ask me all sorts of questions all the time in class. One of my first questions is, what do you mean? And I point out how what they said, there's a bunch of different ways of interpreting it, and you're not really asking me anything. And once I point out why I can't interpret what it is they're saying, they clarify the point that they missed. And maybe they're saying, well, for all ends and for all means, yes, justify the means, and that's what I'm saying.
Zach is the kind of guy that would
Right, he does ask a lot of questions like that.
about everything, not just this question.
Yeah.
Right. And so, a lot of my responses to him are, I don't know what you mean by that.
Yeah.
And let's say exactly what we mean. Unfortunately, we didn't get to do a lot of examples. So, we will start next time with a lot of examples. Let's just do one example to see it all come together. And then we'll call it good. And we'll start next time with a bunch of examples. So, let's try now one that's a bit more convoluted and see if we can encode it now with all this.
Okay.
So I tell you, if one instant of time is after a second, and that means a second instant of time, not after a time interval of a second.
Oh, what?
So that's second as in second place, not second as in
The second.
1/60th of a minute.
Okay.
If one instant of time is after a second, then there is an instant of time after the second and before the first.
After a second, what first?
If one instant of time is after a second instant of time,
So it's the third?
then there is an instant of time, a third instant of time, after the second and before the first.
Ah. Okay.
we're all,
How can it be?
Okay. And it's kind of a weird way of saying it. But you gotta
It's intentionally a funny way of saying it because he's making your second come first and your first come third and your third come second. Let's try it out with a picture. This will clear it all up. So he's saying one instant of time is after a second. So one is after the second. One instant of time is after a second. Then there is an instant of time, right here. Here's a new one. after the second and before the first.
It's a long
So here's the first one.
I see.
So that's what he's saying. He's intentionally saying it in a convoluted way.
in the worst way you could.
Right. He's intentionally trying to confuse you with the sentence so you can read and figure out what exactly the sentence is saying.
Diagrams are nice.
Diagrams are
Yeah,
nice.
they are.
Pictures are wonderful. I don't know how people talk without whiteboards. Unless you have some dirt to draw in.
They just say, I don't know what you're saying.
Alright, so if one instant of time is after a second, then there is an instant of time after the second and before the first.
Okay, so we're gonna try to draw that.
Yeah, let's try it. So let's maybe think what we're going to call these. Maybe we'll use X for that, Y for that, and Z for that.
I would say for all instances of time.
So what are we calling it? Instance of time?
Well, something being an instant of time is a predicate.
So for
No,
all.
it's a
So-
specific instant of time, so you have to do the explanation.
Wait, so we don't have to do.
No, we can just say
We don't have.
X is an instant
There
time.
is no quantifiers.
there's going to be quantifiers.
No, there is.
There's going to be 3 variables, X, Y, and Z, and each one is going to have an associated quantifier.
You're gonna say for all X, Y, and Z, where X, Y, and Z follow these properties, that applies to this must be the case.
Let's try and just get the implication for a second here.
Okay.
So we have an if then, right?
Yeah.
Yes.
So we know, okay, boom, got that.
Yep.
Okay, now if one instant of time is after a second.
Is after is a predicate.
So let's just take that part.
Is
X
after is a
is
predicate.
after Y.
So we got
X is after Y.
X is after Y is one of the things we want. What else do we want?
Then, okay,
If one instant of time is after a second, so first off we need to set their instants of time. So
For all instances of time.
instance of time applies to X, and instant of time applies to Y, and X is after Y.
Mhm.
Then,
You're gonna say instance
Z.
of time applies to Z, and Z is going to
Z
be
after,
the
then
first.
instant of time applies to Z, and what?
Z is after Y. So
Z is after Y.
and you can say X is after Z.
Did you say and?
No, yeah, it would be and.
And what?
You need to say it's before the first. How are you gonna say that?
What was the one we signified? What was our variable for the first?
X. So we need the
So-
before then predicate.
Yeah, so you need a before predicate.
Is there any
So
way of saying it without using the before then predicate? Or do you have to?
I wouldn't try to define before in terms of after on the fly.
Okay, so before the
So,
okay, so then yeah.
right? What? Tell me the letter.
B, and then it's gonna be Z. And then that you're good. For that
Before
part.
Z? The before Z predicate?
Something.
Or no, it'll be what?
Try again.
Oh, it's a two-tier predicate.
There you go.
So
Before
it'll be-
applies to 2 things.
Z before X.
Z before X.
Yeah.
Okay. So we got I is an if, X is an instant of time, and Y is an instant of time, and X is after Y.
That applies.
Then Z is an instant of time, Z is after Y, and Z is before X. Is that what this says?
Oh, we need the
No, we need
quantifiers.
the quantifiers.
What quantifiers?
We're gonna say for all X and for all X, Y, and Z.
Or there
All
just
X.
exists. There's just existence in the
The-
time.
No, you're just gonna say for all X, Y, and Z there exists X, Y, and Z such that this
For all X, for all Y,
Oh.
for all Z.
there exists X, Y, and Z.
Like that is what you want?
No, there
No,
needs to be
there
there,
exists.
right?
Oh, those are, I don't know, you're telling me.
Yeah, so you're gonna say for all X, for all Y, for all Z, there exists X, Y, and Z such that it satisfies that property.
Whoa, so I'm writing 6 quantifiers?
What? No, just the 3.
Oh,
You just went right through.
yeah.
Okay, tell me what I'm writing first. Here, I'll do the parentheses.
For
No,
all,
no,
for
they're
all
not
X and all Y, there exists.
No, it's for all X, for all Y, there exists Z. You're right.
Yeah,
You're right.
Yep, that's true.
You're right. Okay. Yeah, I see that.
yes.
Like that?
Yes.
That seems right to me.
Yes, I think it's correct.
Yes.
Yeah, that's correct.
We all like it?
Yes.
So it's kind of a funny way to write it, but I think it works.
What's the better way of writing it?
Here's the natural way to write it. For all X, for all Y, if X is an instant of time and Y is an instant of time and X is after Y, then there exists Z
Um,
such that that.
That makes more sense, yeah.
Because the way you want to say it is, for all x, for all y, there exists a z such that if x is an instant time and y is an instant time and x is after y, then z is an instant time and blah, 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 blah.
That makes sense.
So, I'm 95% sure that the way you guys had it still works,
Okay.
but it's just not a very natural way to write it.
It's not,
Natural being appealing to my intuition. Maybe there's someone that just seems more natural to.
it's really good question of computational speed.
We just want is accurate. Starting with rigor. We worry about performance after you get working.
Yeah.
Alright. Sorry, we went a little bit long, but want to do at least one example with something more complex. So next time, we'll start with a bunch of examples and then we'll jump into the next thing. Doing proofs basically with quantifiers after this. Because we got to figure out our rules for working with quantifiers now when we prove. Any questions you want recorded? Anything before next week?
No.
Alright, see you guys next time.
Thank you.
Yep.
Mondays, from now on.